Okay, so continuing with this lecture on abstraction, adding abstractions. So the next thing we need to consider, we've talked about the environment, is the stores. And our stores are a little bit different from Hoodle, but not much. What we did instead, what he does is he keeps track of the next open memory position in the store back in the environment for variables. But suppose that we wanted to keep, I guess we could always look it up there, but it seems easier when we have multiple environments. Suppose we had an environment that corresponded to declaring an array, for example. Well, that one might need to know what's the next available location. If it's stored in the variable environment, then I'm going to need to pass around the variable environment. So it seemed more reasonable to put the next location to keep it in the store. And it turns out, for kind of debugging reasons, we also would like to know the max size that the store ever got to be. So, first of all, a store is a map from locations to ints. And remember, locations are just an int. So we have that, type loc equals int. So this is just an int to int map. And so what we do is we never expect to actually store anything in negative value, negative memory locations. And so we reserve two of them. We use -1 to be the next loc, and we use -2 to store the max store size. And so this is like private memory locations that should be unavailable to users. Now, this means that to make an empty store, I have to initialize those things. And it turns out that from list is, I can write down the type of it here. From list, it's in the map library. It takes a list of A-B pairs and returns a map from A to B. So to set up the initial store S0, what we do is we say, but next loc, which maps to -1, has the value 0. In other words, the next available location in the empty store, S0, from the initial store is location 0. And the max store size, similarly, is set to be 0. So this is an empty store, but it has two values set. Those negative input values, -1 and -2, are set to the appropriate things. Now, if you look in the book at the I'm trying to, find the page where he does all this, is, the var declaration. So it would be in the var declaration. He's kind of keeping track of, so you've got the semantics of variable declarations, but he's also kind of building in this allocate function. And so we can simplify our statement for declaring a variable, like here, by writing an allocate function. So the allocate function takes a store, and it returns a new location that hasn't been used before, and it returns a new store that has that location initialized to some value. So here's what we do. We say, okay, take the store that you were passed in and look up the next location, and that's the new location L. And now create a new store by inserting into the next loc L plus 1. So it's going to point to location plus 1. And where do we do that? We do that in the original store that was given in. So now we've updated to make sure that next location remains consistent. We've allocated a new location, and the next location position in the store, which is what, -1, is now whatever the next location was, +1. And then S single prime, which is what the answer up here is going to be, is now fix the max store size. So we want to keep track of how big the store ever got. So we insert into max store size, location -2. We take the maximum of L plus 1 and what was ever in the original store, look up what max store size was there. And if that turns out to be bigger than where we are currently, then, retain that. Otherwise, if it's growing beyond the former maximum storage size, use that. And where do we insert that? We insert that into S double prime, the one that has the correct next loc, and then we return, that gives us S prime, and that's what we return here is S prime. So this is allocate. So it basically does the bookkeeping for us of keeping next loc and max store size properly updated. Now, max store size really isn't necessary, but like I said, it's useful for after running a program, being able to sort of examine the memory effect. And you might wonder, why would it ever be that the next location shrinks? And that's the begin-end block, because the next location will go back to whatever it was in the previous one. Okay. Now, this alloc function simplifies the semantic rules because we don't need to keep track of next and how to maintain it in there. So let's look at the new syntax. So what we have is we have statements, and we've added a begin-end statement, and we've added a way to call a procedure. And then the declarations are that we can declare a variable or we can declare a new procedure. The name is P and the statement that we're binding it to is S. In a variable, the variable name is X, and there's an arithmetic statement to initialize it. So this syntax is different from what he does, what Hudl does. Did I talk about that down below? Yeah, I mean, here's Hudl's, his syntax is, he has this syntax, he has two separate declarations. He has DV for declaration of variables, and he has DP, and then we'll see in a minute down here his meaning and how he keeps track of everything. So, but for now, our syntax is we have this and we have this, and then what we've done is up here in the declaration, in the begin end block, we've made a list of declarations. And so that means that they can come in any order. You can have a variable declaration and then a procedure declaration and then another variable declaration or another and then another. So in any order. I found it also in his code here, for example, you have to have variables declared before procedures. Now his code will work. The new syntax subsumes that. But you always had to do your variables before your procedures, which just seems silly. I mean, here, why do I need to have this procedure P declared before I declare variable Y if it doesn't even mention Y? So this is an example program in this language. So you can see now we can write kind of reasonably complex pieces of code. Let's try to get rid of some of these highlights here. That always happens. I don't know. I wish there was layers here. Proc P. Whoops. Okay, so let's just look at this code. We come in and we declare a variable x and initialize it to 0. And then we declare a variable y and initialize it to 0. And then we declare a procedure P, which is x equals x plus 3. And then we declare a procedure Q. That all it does is calls P. Now, and then this is all declared inside of, we've got in, and now here's the body of this begin end block. Now we've got another begin, which redeclares a variable x. And now P is x equals x plus 1. And so then I call Q. Now this is this is where we get into some complicated issues on how scoping works. So you might say, okay, look, I'm calling Q. Q is defined up here. Q calls P. But the question is, which P does it call? Does it call the last P? Does it call the last P that was declared, this P? Or does it call this procedure P? Now, most of you would probably say this one, because that's what happened in virtually every programming language you use. There were some early versions of Lisp, and I think Emacs Lisp, for some reason, would still have this Q referring to this P. So that's Emacs Lisp, is the Lisp that's built into Emacs for programming macros. But really, probably static scoping rules would say P refers to the P that's there. If P refers to this P, it's quite a bit different, because now then the question is, which X does this refer to? Well, this X is going to refer to that X, and this X is going to refer to that X. But this X is going to refer to this X. So, and that X refers to that X. So we could have a mixture of static and dynamic scoping rules depending on what kind of thing that we're looking at. And so that's really makes things exceptionally complicated. So, and then down here, the last statement says Y, and so that has to be this Y, because we didn't even declare a Y down here. No Y is declared in the body here, but this X should refer to this X right here. So anyway, we'll look at another program in a few minutes, but you can try and evaluate this one and see what the difference in the answer is, whether Q calls this P or does Q call this P. Now, to make it so that this Q calls the P that was up here when Q was declared, we have to do more than just put the statement for a definition in. We need to say, oh, and here, by the way, when we store away Q, we need to store away the environment that was in place at the time of the declaration. So we'll see that later in the next lecture, how that affects the environment and how it affects the call command also. What do you do when you call? So let's look at the semantics for something simple like A expressions. How are they affected? So the A expressions stay the same. We don't have any new A expressions. And so in the old version, we had when S was a function that mapped a variable to an int, we wrote S and then a turnstile, and then X gets updated to V in the semantics for A expressions. If, when I apply S, which is a function that maps variables, to the variable X, when I apply S to X, I get back V, then that means this goes to V. But in the new model, we have to look up the value of a variable in the environment to find the location where it is, and then you need to look in the store to see where it is there. So now rules look like this. We need both the environment and the store to evaluate an individual variable. And so what we do is we say X goes to V if when in the environment I look up X, the variable name X, I get the location L, and then in the store, this store here, I look up L, I find the value V stored there. So it turns out that this is the only rule that actually looks things up in the statement command, in the language of statements. Now, all the other rules have to, like before we ended up carrying S around everywhere, now we have to carry around the environment and the store. So, for example, the rule for a numeral in A expression just returns K, when you figure out that numeral N actually is the numeral representing K. And the other rules look similar. We have to always have an environment and a store, an environment and a store on all these different rules. But here's the one for the various operations, plus, minus, and times. Here's the one for parentheses. So we can do a little example derivation. Suppose that the environment in the environment env X maps to location 1, and store STO location 1 maps to 42. Then we can say, okay, in that environment and that store, X plus 1 evaluates to 43. Why? Because the rule says, okay, evaluate X over here and evaluate 1 over here, and the numeral 1 evaluates to the integer 1, and on this side, the value X in the store is 42, and that's because store composed with env applied to X yields 42, so 42 plus 1 is 43. So this derivation justifies the claim that in environment env and store STO, the expression X plus 1 is in the A-hour relation with 43. So in other words, X plus 1 paired with 43 is part of this arrow relation, assuming env and store have the particular properties that we set above up here. We specified some values in env